It sounds like we're going. So I'm going to do something interesting. Okay, so we left off right. Okay, wait a minute. We left off back. Anyway, let's see somewhere. Yeah, we left off right there. What we're going to do is look at something else and as a kind of an example, and let's start with a case, and I do this only to set us up for a section in the book. Let's say you had an object that was sitting here, and we're just going to make the load pretty simple. 100 pounds. And the distance or the vector out to it, I'm sorry, x and a y. So the vector out to it, I'm going to say, is just 3i plus 4j. So if we want to find the moment of this thing, we would just do this. It's a pretty simple thing. I, J, K, and the R vector is 3, 4, and nothing, and the F vector is nothing in the X minus 100, or maybe I should have just made it 1 pound, but it's okay. So in fact, what we get is an I that has, you X this out and this out, you're only left with this. And you would get a 4, 0, minus 100, and 0. If you X'd out the J, I'm doing this just to be complete. You would take this and put down here, and it would be 3, 0, 0, 0. First thing you're going to see is you're going to get a 0 and a 0, 0 and a 0. The only thing left is the K, and it's going to be Xing these out, taking that, put over here, 3, 4, 0, and minus 100. So out of this, you're going to get your moment being, that's going to give you nothing. This is going to give you minus 300K. Now, I'm going to do this, get you used to something. Okay, so if you have an X and a Y, this is a positive moment there. So in fact, the fact that you have this being minus 300 means it's going clockwise, and it doesn't become too strange to see that this is 3 in your moment arm. You could use transmissibility to take that load, move it down here, you would have 3 times it. No, leave it right there for the moment. Now, there's nothing new, nothing fancy. You can do the transmissibility, you can look at it that way. Here, I'll even do it this way. Kind of copy it and say, hey, there's my 100. Ooh, interesting. There's my 100 there, and it's 3 over, so that's a 300 moment going this direction. Same thing I would get right here. Got to take another case. Now, to take that same 100 and I'm going to move it over to the right. This time my vector, my R vector. This time I'll say, hey, well, let's see, now it's 10i, or oops, I said 10, I wrote 100, plus 4j. So I simply moved it over to the right. Now, you can go through the math, but you'll end up with 100 times the 10. Now, if we want to do that, let's do it real quick. And the way I'm going to do it is I'm going to make use of what I did before, but I'm going to adjust things a little bit. So I'm going to take this, do a copy, and do a paste. I'm going to drop it right here, change everything to, oh no, well, anyway. So this time I'm going to take all this one out because I know it's going to be 0. I'm going to move it back here. And this time, I'll zoom in on it. Well, what happens different? The 3 goes away and a 10 is placed there. And, not too surprising, you get that. So, same thing you would have got if you would have done this and used the transmissibility, which basically says, and let's see, I can now select, I don't understand why that is, and basically go move this 100 pounds anywhere along this line of transmissibility. We're going to do something different now. And say, okay, now I have 2 forces. So in order to have 2, here's what I'm going to do. I make use of the magic of this copy and paste. We're going to change our problem. I'm going to move down here now, drop this. So what I'll do is I'll kind of separate this. Okay, here's your first situation. Here's your second situation. Now I'm on to the third, and I'll box it a little bit. This time, I'm going to do something interesting. I'm going to say, I got 2 forces now. I'm going to keep up with my 100. This time, I'm going to sort of extend this up here. And I'm going to put another force that goes up here, and it's 100 pounds. Okay, now it's R. It's going to be pretty simple. It's R. It's going to be, I'm not moving any in the I, so it's going to be 4 times a J. So again, I'm going to make use of this, the fact that this is the case. Go ahead and zoom in, get rid of those 2. I'm going to copy this over to here. So I got my 300, but now I've got another force here. Okay, I've got an I, a J, and a K. This time, so I've got, this is going to be called R1, and I'm going to say I'm R1 and F1. This is 2. Okay, hello, okay. Cross F2. This one will be F1. This will be F2. This is 1. This time, this is 2. So, what do we have? We have nothing. We have 4. We have nothing. This time, I've got 100 going up in the y direction. My 4 has to do with this. There is no I and there is no k component. So I end up with that. Lo and behold, interestingly enough, if I pull out my k component, because that's the only thing I'm going to have, I'm going to have 0, 4, 0, 100. So this term right here adds nothing to it, and I get still the same 300. Now, let's take a second romp to this. Okay, now I can draw the box around it, but I'm going to go down, say maybe drop it right there, maybe slide it over. Okay, I'm going to start monkeying with it, but before I do, I'm going to solidify this and say, hey, there's an example. Now what I'm going to do is pretty interesting. Let's see if I can go out here and move some things to the right so that I can mess with my drawing. So this time, I'll go ahead and take some of this off. Go ahead and take this off. And I'm going to see if I'm able to do a decent selection. And I'm going to slide it to the right. Now, okay, my R1 looks a little bit different. Let's say my R1, oops, that's not the, let's go in here and go back to red. So here's my R1, and here's going to be my R2. Now, since I moved them together and they did not move any further apart from each other or closer together, my R1, I'm going to say I moved it over. Now it's 10i. I think it was still 4j, so I want to keep my 4 here, although it plays no role. And my R2 now has a distance over. Now, here's the thing. They were up here, they were 3 apart. In other words, the distance, see if I can use some other, yep. The distance from here to here was 3. So I'll maintain that distance of 3 from this point to this point. So if that's the case, then this is, okay, this is 7i, and it's still at the 4j. So now my forces did not change, but my r's did. So let's move out here, and we realize we need to change this one, we need to change that one. So for R1, I grab this. It would be 10 and 4. For R2, I grab this one, which would be 7 and 4. Now, this doesn't become 0. This and this gets changed. This gets to 10, and this gets to 7. So now, let's move this down. And now we need to work on this one. Okay. This times that, not going to give you anything, but that times that's going to give you minus 1,000. Okay. Plus, this and this gives you nothing, but that gives you 700k. Add those together in your moment from those two forces become 300. Hey, wait a minute, it didn't change. Now here's the key. If I take a single force, like I did, move it to the right, I did, I get two different moments. The first one is 300, the second one was 1,000. They're both negative. So now I put them together. I put another one that's opposing. The rule is if you're going down on one, you have to go up on the other. There has to be a distance apart. Now I took both of those forces, moved them to the right by 7. And guess what happens? The moment doesn't change. Let's even go further, okay? I am going to copy this thing again. Okay, but before I do, I'm going to designate, hey, this is its own entity. And now I'm going to copy it. We'll copy. Oh no. Okay. Okay. Copy, not a delete. Okay. Put it about right there. Now I'm going to work on it. And this time, I'm going to arbitrarily take these things. First of all, I'm going to move this up and out of the way. Up on top, maybe. Okay, now what I'm going to do, I'm going to take those forces and move them in any arbitrary position. That actually is going to be hard to draw my vectors, so I'm going to move it over here, say. Now, the key is a couple keys. I moved them in unison, and I kept the 3 distance the same. Okay, so now I can go in, do my R1 vector. This time I'll say R1. Now what I'm going to do is kind of weird. Let's say R1 is I don't know, some value. I'll say I move it back here some distance x1, so it's some distance x1 here. So I'm making it a variable now. So oops, shouldn't be x1 minus y1. So this distance would be the distance down to here. This will be y1, some arbitrary distance. X1 could be 1,000,000. For that matter, we could put in 1,000,000, but I'm just going to carry it as a variable. This time R2 is going to be, what is it going to be? Minus x1. Going to be slightly further back to the left, minus, now y1 is still the same. So these two line up here, and this is still the y1. So now, this variable x1 or y1 could be anything. So now I've got some bizarre thing where I can move these anywhere. I can insert x1 and y1 to be any value that I want. So here they are. And now I'm going to insert them. Now no longer does this matter. I'm going to insert them in this equation. Now to do this, I'm going to have a little bit of space here. So first of all, what you notice is the R1 goes in right here. So this is going to be this minus y1. And this one's going to be, this is going to be easy right here because it's going to be minus x1. It becomes harder on this one because I've got to write a little bit more refined here. So here's your minus y1. But in this I, I've got to insert this. Minus x1 minus 3. So I'm going to put a box around it. So what happens is you get minus x1 minus y1. What you notice is, doesn't matter where y is, because you multiply that, it gets 0. So what you get here is, now I have this as a minus, it really doesn't matter, but this is a minus 100, but I'm multiplying it times that, oops, and so I get that. Now I've got to go in here and do minus x1 minus 3 minus y1. Guess what? The y doesn't matter. So what you get out of here is this one times that one. 100. I'll carry it as a 100. And then I'll carry it as a minus x1. You know what? I think what I'll do is split them. Minus 3 times 100. First thing you see is that this cancels that. And guess what you get? You get back that. So in effect, this is a very interesting thing because this is something that's called a couple. Meaning you have a force anywhere in a plane. Give me a second. Anywhere, doesn't matter where it is. If you get a force here with some F going down, and you get an F going up here, and the distance between them, then the moment, everywhere, anywhere you place this couple, I'll do it this way. So anywhere you place this couple, the moment is equal to F dotted with times D. And what you realize is I can go ahead and put a direction because I see this thing going like that. So there's this. Guess what? It doesn't matter where I put it. The moment doesn't change. So a couple has that ability. Move it around wherever you want. It's still the same moment because it's a couple. It has an offset there. So anywhere you put it, it's the same. Now let's go back and look at the book and see what he says about this. And okay, so here he's talking about a specific axis. I probably should have done that first. I think the couple might be behind me. Let's see. Okay, now it's right here. Now I'll go back about the specific axis in a minute. So here's what he's saying. So now that you've seen it mathematically, you know it doesn't matter where you place it. So if you do this moment together, you get that. Doesn't matter what RA, RB is. It just matters the distance between. So this is what it's got. So when you have a couple like that, all you have to do is come up with the moment. That moment can be placed anywhere. So here's a typical case in point. 40 times 3. Well, that's the same as 30 times, well, I should have said 40 times 0.3. It's the same as 30 times 0.4. So in fact, the further apart these are, the bigger the moment's going to be. You get out to a certain point, and at a certain point, do you really need to put those on there, or do you need to just say this? Somebody's twisting it. For example, do you need to really say this? Do you need to draw this and say this? Or can you just take this little drawing, put the point right there, so this point is right here, and then just say, oh, I got 40 times 0.3, or same thing as 4 times 3, or 12, or I've got 30 times 0.4, which is, 3 times 4, which is that. So it's 12. Or do you just want to say this? Is this good enough? I've got a twist or a moment about this point. He didn't label it, but I'll label it A. So I got 12 that way. Well, he starts doing it like this. Then you start realizing, oh, wait a minute. If I have a couple of couples, this sounds weird. more than one couple, let's say, okay, well, he's kind of done it here. So here you got two moments, two couples, the vector pointing this way, twisting about this. You add those together in a vector sense, and you get the resultant. Now, it's kind of, you can barely see it, but there's a twist like this direction. Now, it turns out this one's going this way, so if you point your thumb in the direction in, you're curling your fingers in a rotation for your right hand. You do the same thing here. Point your thumbs here and rotate your right hand in that particular direction, and that's what you get. So then, if in fact this were a negative, it would go this way, and the couple would go like that. So in other words, you would point your thumb this way, and you'd rotate your fingers of your right hand this way. And in that case, if this didn't exist, then the resultant would be, I've done this, would be off in that direction. So look at this particular point. All you got to do is find out where your couples are. Okay, I got a couple right here. Okay, so I'll just list them here. I'm not going to pay attention to what he's got. 3 times 5. It looks to me like this goes this way. So what do I got here? I got this one. Now notice, they don't have to be, in other words, line of transmissibility means I can take this vector and move it up to here. So all I got to do, is find the distance between them. So I've got a 200 times 4, and it looks to me like it's going that way. And then I got a 450 times 3 here, and it looks like it's going this way. Now I've got them all separated, but what he's decided to do, let's see if he followed the sign convention. X, Y, this being positive. So you got a positive, you got a negative, and you got a negative. So did he follow that convention? Okay, I got my positive, it's right here. Got my negative, which was the 204, and then I got my negative, which was right here. So yes, he did follow the sign convention. So here's a particular case. You got a gear trying to transmit torque or moment from, say, over here to over here. So the first question is, what moment is being transferred? Well, you've got a portion here, and you got a portion here. You got a portion here, and you got a portion here. Now, turns out what he's done, it's 600 on both, 30 on both. This is the same as that, and this one is the same as that. So what he's got, okay, so let's put our sign convention down. And this is a positive. So what I've got here, this one together with that one is producing something that looks like that. And that's value is, it's 0.2, because the distance here is 0.2 times 600 times 30. And is it positive or negative? This one actually is negative. And then I got this one, and an opposing, the same distance apart, just here, 0.2, 600, cosine 30. Now, what does it look like? It looks like, to me, it's moving this way, or it's moving in a positive sense. So is that what he's got? He's got the 0.2, 600 sine of 30 with a negative. That's this one. 600 cosine, positive, and that's this one. Now, what he's done also, and you can do this if you felt like you wanted to, forces go down towards each other if you could figure out the distances. Now, if you wanted to, you could figure out the geometry to figure out the distance. I'm not sure that, I mean, you could do that, because you could put a vector from here to here. And this sounds weird, but you could put a vector in this direction, and then make it a base vector and dot the two, and then you could find the distance there. But whether you want to do that or not, that's up to you. So I think these are other problems like that, but let's just go down and find one of these. These are the F problems. Okay, so determine the resultant couple. Here, that one's maybe too easy, so I'll do this one. I think, yeah, I just use the same page, So here, let's go with this. So here's my new problem. I'm just going to drop it like right here. Well, I guess I'm obviously going to have to zoom in on it. Okay. So we look at this, and both of them are 10 kilonewtons. So if you wanted to, multiply this times 2, this times 2, that gives you 8, and this times 2, that gives you 6. This one. Multiply times 2 gives you 10, 2 gives you 8, 2 gives you 6. So there's your two individual couples. We'll do the 8 first. The perpendicular distance between this 8 and that 8 is 4 times 8. Now, which way is it going? When I get my, just write down, I just do this as a force of habit, if this is positive. So the X and Y coordinates I put there in order to remind me why it's that way. So what is this doing? This is actually doing this way, which is actually a negative. Now, the distance between the two 6's perpendicular distance is the 1 and the 1, and it's producing a moment this way, which happens to actually be positive. And so you get, okay, 32. I really should have done this like M1 and M2. So here, this will give me the same thing as 32. Putting those two together, that goes back together to give you minus 20. Now, let's do it the other way. I'm going to do it the hard way. Oops. Okay, this will take a little bit of thought to this, okay? I'm going to check myself to see if that's the case. Hey, what I'll do, I'll try to copy, yeah, let's try to do this, copy, because I don't want to mess up the drawing here. But what I'm going to do, I want to figure out something here. Did I just move the picture or the, there we go. So what I want to do, I'm going to basically draw a line in this direction. So I just want to draw a vector like so. So that vector, and I guess I'm going to have to pick a location for the coordinates. Okay. So I've got this vector that goes in that particular direction. I really want to know, okay, since I put this in that way, this will be a line. It's going to be a line that's going to have an intercept. I'm going to draw it this way. Here. Y is equal to rise over the run, rise over the run, 4/3 x. The intercept of this line, I've made the origin go through there. Now I'm going to draw a vector to that point. So I don't know what to call this except to call it R. And that vector R is going to be that vector R is going to be going over to the x of 4 and up to. Now what I'm going to do this. I am going to, I could have used a ruler here. I'm going to draw this. So what is this line? It goes through the origin too, but it's a negative slope. But what I really am interested in doing, what I want to do, this looks weird. Let's do the unit vector in this direction. And then what I want to do is I want to take this vector, a vector this direction. Let's take a unit vector in this direction. We'll call this unit 1, and I guess I'll call this unit 2. So here, let's go back and figure out unit 1 will be, it moves to the x of 3/5 I plus 4/5 of j. In other words, I'm using the 3/5 to the right and 4/5 up. Now, I want a vector u2 which is perpendicular to u1. Oops. So how do I do that? Well, okay, this vector moves up as well, but it moves back to the left. Moves back to the left, 4/5 I and 3/5 j. Now, how did I write that? Well, first of all, I noticed, okay, I'm not able to select. I don't know why it does this. That's interesting. Okay. Okay. So what I was able to do, I'm able to take this, move it here, put a minus sign on it, because it does go back to the left. Then I notice this and this. Okay, so the reason this always works, in which if you look at u1 dotted with u2, I get 3/5 times a minus 4/5. Taking this number comes this number, and then I add this number times that number, 4/5 times 3/5. So in fact, my goal here was to find a vector that was perpendicular to this line. In fact, 90 degrees to that line. Why do I want that? Here's why. Let me get rid of some of this blue. because I want to be able to take the vector that is r here, and I want to dot it with that. Okay, so here's what I mean. If I dot this, okay, and actually I can take this u and turn it the other way too. If I turn it the other way, u2, I'll call it u3. It simply goes 4/5 I minus 3/5 j. Simply goes to the positive x, negative y. So both this vector and this vector are both perpendicular to this one. So if I dot these, let's see if I write this out. Here's r. Here's the unit vector, u3. And let's make a triangle here. Now, if I'm going to dot this, in other words, r dotted with u3, what do I get? A length of r, length of u3, cosine the angle between them. So in fact, this, nothing but 1. So this becomes the distance right there. Well, if that's the distance, that's the same distance as the triangle here and the triangle here. So in fact, taking r, which is this, 4i plus 2j, dotted with this, 4/5 I minus 3/5 j. It's a long process, but what we're doing, that would be 4 times 4/5 plus 2, minus, because there's a minus here, minus 2 times 3/5. What's that equal to? Equals to 2. Wow. So the distance between these is 2. I did all that work, but I found the actual distance between these two forces. Now, if this distance is 2, let me copy this sucker again. Copy. This time we'll drop it right there. Then this force that sits right here can be copied along its line of action. Put you right there, and it's still 10. And the distance between these things is 2. So it goes this way. Remember what positive is. Positive is that way. It's going the opposite direction. So it is 10 times 2, which is the same number that you get right back here. Now, this exercise that I did here is kind of a geometric exercise, and you know, this, what I did here to find this 2, it's something you can do all the time. If you are looking for 2 vectors, you know, if you have vector anywhere, you put your coordinate there, then you have some vector over here. It's got to be going in the other direction. So this could be 100, this could be 100. And then you draw this. Oops, I missed it. Then you draw this R. Then, if you can figure out this vector, the unit vector in this direction, then by nature, what you are doing, not switching again. Well, then I'll tell you what we'll do. Let me just switch colors on you here. What you're doing is this. Once you have your unit vector in your R, you take your unit vector and dot it with your r. It is the length of the unit vector, the length of r, times the cosine of the angle between those two, which you do not have to have. You just recognize that it is a triangle that exists right here. This is your triangle, and this is a value of 1. So this is the distance, r, and the cosine. Then that, for this triangle, you have to realize 90 degrees now. This becomes u dot r, or it becomes the distance r becomes cosine of the angle between it, which you don't have to have this. You just have to find that. So this is how you find the perpendicular distance d between any two vectors in any orientation. You put your coordinate system on one, you go a vector to the other, which you did, then you find its direction, the force's direction, and you come up with a perpendicular unit vector, and that's how you find your perpendicular distance between those two. It always works. It's a little bit of extra math, but in the heat of the moment, if you have the time to do a check, this is a way to do a check. Okay, so what we did, we covered couples. We realized that first thing we did is we realized if we move a force just anywhere on the plane, just move it over, you get a different moment. Then we realized if we threw another opposing force a distance away, we found the moment due to both forces. Then we realized we can move it. We move it over to the right. We get the same moment from that. What we found out later to be a couple. Then we move it randomly anywhere. We still get the same moment, and we realize we can move this couple anywhere. The moment's going to be the same. So we can move it anywhere. Doesn't really matter. The moment is still m is equal to f times d. Then you got your positive negative that you got to think about, which is kind of right here, and I do that over and over. Then I took a particular problem, I found it, but then I want to know the perpendicular distance. It turns out, and apparently I can't select anything, but it turns out that you can follow this standard kind of procedure to always find the perpendicular distance. And that procedure is a unit vector points opposing direction, or I'm sorry, you have a force, one of your forces, put your coordinate system there, anywhere along it, you'll have the coordinate, you'll have a direction, you find a unit normal, not a unit normal, a unit vector which is perpendicular to the line of action, called it a u, just dot it with the vector. The results comes out to be the distance between them. You just take that distance, multiply it times the 100 pounds, or whatever it is. In this case it was 10. The perpendicular distance was 2. Worked out. So I think we'll call it good.